Hey everyone. In this video, we're going to be talking about some common monosaccharides. We'll be looking at the chirality centers in the monosaccharides, how to draw them as Fischer projections, and the D versus L notation. And by the end of this video, you should be able to identify a monosaccharide as D or L. And so let's talk about what all this means. So monosaccharides have one or more chirality centers. We learned about chirality centers in a previous video. Glyceraldehyde, the simplest aldose, has one chirality center, and therefore it has two possible stereoisomers. And the two different enantiomers of glyceraldehyde are shown here. And so the central carbon is the chirality center. And so you can have it with the OH group on the right or the OH group on the left. And so when the OH group is on the right, we call it D-glyceraldehyde. And when it's on the left, we call it L-glyceraldehyde. Now, you don't really need to know where these terms come from, but they originate from the terms dextrorotatory and levorotatory. And so as it turns out, one of the unique properties of stereoisomers is that when you shine plain polarized light at them, they will bend the light waves in opposite directions. And so Louis Pasteur was actually the one who discovered this. So he was working with these two versions of glyceraldehyde, and he discovered that this one rotated light clockwise and this one rotated light counterclockwise. And so the Latin terms for that were dextrorotatory and levorotatory. And so to abbreviate that, he used D and L. And so that notation has carried on to modern day. And so we can define sugars as either D or L, which is describing their chirality center. Now, drawing these with wedges and dashes can be a little bit tedious. And so we have a simpler method of drawing these known as Fischer projections, named after the chemist Fischer, who discovered or came up with this method of drawing. And so Fischer projection is a 2D representation of a 3D molecule. So a chirality center is tetrahedral. And so if we orient this carbon to where the two groups on the left and right are coming towards us, and the two groups above and below are going away from us, we can imagine ironing this flat and just drawing it as a plus sign. The chirality center is where the middle of the plus sign is. So kind of like a skeleton structure, right? Anywhere two bonds meet, there's going to be a carbon there. And so this is the Fischer projection of this molecule here on the left. So the chiral carbon is always located at the intersection of the cross. The horizontal bonds are coming towards you, and the vertical bonds are going away from you. So a Fischer projection is this 2D representation of this 3D structure. Now, let's see how that applies to sugars. So if we take our L and D glyceraldehyde, we can press this flat and draw it as a Fischer projection. And so the chiral center here is just drawn as a plus sign. Okay. And we can see here that the OH being on the right is our D glyceraldehyde, and the OH on the left side is our L glyceraldehyde. Now, the Fischer projection for bigger sugars will have more than one chirality center. So you always place the most oxidized group at the top, meaning your aldose or your ketose has the aldehyde or the ketone at the top of the sugar, standard notation. The chiral carbons are going to be all these plus signs here. And so the hydrogen and the alcohol groups will be either on the left or the right for each chiral center. And then the last carbon is not chiral because it has two hydrogens attached. And so we just write this as CH2OH because it's not a chiral center. So here would be the Fischer projection of glucose. And you can see highlighted in blue, it has 4 chirality centers. The aldehyde is not chiral, nor is the CH2OH group, but everything in the middle is a chiral center. Now, the L and D notation makes sense when there was only one chiral center. But when you have a bunch of chiral centers, how do you know which one to go off of? And so the answer is you go off the chirality center furthest from the carbonyl, so the one at the bottom. So the bottom chirality center is what dictates D or L, right? And so if the OH is on the right, it's D. If the OH is on the left, it's L. And so you look at the bottom chirality center. And so in this case, the OH is on the right, and so this would be D, glucose. So let's do a quick study check. Identify the following monosaccharides as L or D isomers. So we're going to look at the bottom chirality center. If the OH is on the right side, it's D. And if the OH is on the left side, it's L. So this would be a D sugar, and this would be an L sugar. Now, it's important to note that all naturally occurring sugars are D sugars. I'll repeat that. All naturally occurring sugars are D sugars. It's not a coincidence. So the last part of this video, we're going to look at 3 really common monosaccharides: glucose, galactose, and fructose. And they're really important for many, many biological reasons. These are probably the 3 most common hexoses. So glucose is an aldohexose that has the following orientation of the chirality centers. Galactose is another aldohexose. The only difference is the chirality here at carbon number 4. You can see that in glucose, the OH is on the right. In galactose, the OH is on the left. So these are stereoisomers. And then fructose is a ketohexose. So it's a structural isomer of glucose. All right, so let's look at glucose a little more closely. Glucose is the main product of photosynthesis. It's the most abundant sugar on the planet. It's found in fruits, corn syrup, honey, it's found in wood, it's found in starch. It's the most abundant sugar on the planet. It's also known as dextrose in medicine, and it's also what we refer to as blood sugar in the body. So when we say blood sugar, we're literally talking about glucose dissolved in your blood plasma. And glucose is the building block for larger, more complex sugars like sucrose, lactose, maltose, and starches and cellulose. Galactose is another very common sugar, but we don't usually find it by itself. We usually find it paired or bonded to glucose as lactose, so in milk. So galactose is one of the main components of milk sugar. And then fructose is probably the most common ketose in nature. It's the sweetest tasting of all the monosaccharides. It's about twice as sweet as table sugar, actually. So it just binds to your taste buds better, and so it tastes very sweet. It's found very commonly in fruits and in honey, which is why fruits and honey taste so sweet, even though they don't necessarily have any more sugar than other things. So yeah, 3 common sugars: glucose, galactose, and fructose. And we will take a look at these more closely in some of the upcoming videos. Well, thanks for watching, and I'll see you in the next one.